Hello, welcome back. This is our second lesson about eigenvalue problems. And the next time, we're going to look at the applications of eigenvalue problem and finish our first module on matrix algebra. In this lesson, we first will look at more examples of the geometrical meaning of eigenvectors. And then we're going to talk about eigen decomposition and some propositions of eigenvector. And then we're going to look at how we're going to apply the eigen decomposition to reduce computation. Finally, we're going to look at a few MATLAB codes and see what we need to be careful and what kind of mistake we can make. Let's review the geometrical interpretation of eigenvector. If we think this matrix A is the linear transformation, and when you multiply A to the vector, the result is the image after the transformation. If we have A times V equals lambda times V, well, the lambda is a scalar. This means the image will stay either the same line or the opposite direction of the original vector V. Such a vector, we call it an eigenvector. Of course, we don't count when the V equals all zeros, because that's trivial, not interesting. 0 times anything equals 0. So both sides equal 0. It's not interesting. A nice example I showed in last lesson is the mirror reflection. In this example, I hope you still remember there's two eigenvectors. One is this vertical vector. This vertical vector, if you do the mirror reflection, is unchanged. That means if this vector V, let me call it V1, equal 1, 0, or it could be 2, 0, if you make it a little longer. And after the transformation is the same, V. See, there's no reflection because it stays right on the mirror. If you feel this position, 1 times V, you realize this lambda equal 1 is the eigenvalue associated with this eigenvector V1. There's another one. The other one is this horizontal vector. We can call it, the V1 is 1, 0, 1. And the next one is 1, 0. If I call this as x1, this x2. Well, the mirror reflection of this V2 is going to be the opposite direction. And it will be negative 1, 0. So we have this A times V2 equals negative V2. So you realize that this lambda 2 equal negative 1 is the second eigenvalue. That's an example. You have two eigenvectors. So it's very nice. Let's look at another example. This example is called the diagonal stretching transformation. And the matrix is A equal 2, 1, and 1, 2, a little calculation, we can find that this x equals 3, negative 3 is an eigenvector. Let's do the calculation. If we multiply A to the x, 3, negative 3, so the first row times the first column, 2 times 3 plus 1 times negative 3, that's 6 minus 3 is 3. If you multiply second row to the first column, and so 1 times 3 plus 2 times negative 3, 3 minus 6, negative 3. And then we realize this is an eigenvector associated with the eigenvalue lambda equal 1. Let's look at a simulation to this let me see if it so transformation, look, means change the shape. Transform means change. See, look at the corner. The original rectangle is stretched along the diagonal direction. Then you can observe 3 sets of different vectors. One is blue, is parallel to the diagonal. Another one is purple, is perpendicular to the diagonal. And the third group is red in all other directions. Now, pay attention. Which one did not change direction when you are stretching doing the transformation? And then we're going to come back to the calculation. Well, if you write down the previous example, the vector 3, negative 3, you know, this is the vector with the purple color, perpendicular. This is the diagonal direction. Negative 3, negative 3, so 3 here, negative 3 here is this direction. See, it's perpendicular to the diagonal direction. And this perpendicular direction clearly does not change if you stretch it to the diagonal direction. That's the purple one. If you look at another one, the red one, which is 1, 0, and 1, you can see the 0 and the 1 is that red vector. 0, 1 is the upright direction. This upward direction, if you multiply the A, you do the same calculation. 2 times 0 is 0, 1 times 1 is 1, then here's 1, 1 times 2, 1 times 0 is 0, 2 times 1 is 2. So after the transformation, this vector become 1 and the 2 become this direction. See, that's how you stretched it. So it's not an eigenvector because it changed direction. I don't know if you look at this simulation carefully. Can you name another vector does not change direction? In other words, the other eigenvector. What is it? If you pay the attention. Now, think about this question, then we observe it one more time, and you should get the answer. So When you stretch it, see, we got this purple direction, which is the same as 3, -3. Does not change direction. And this red one, the red one in this corner is changed. See, the direction changed. And now the answer to the question I asked is this blue one. Even it is stretched, but does not change direction. Let me do a little more calculation for the second eigenvector. I can call it 3, 3, the diagonal direction. If we multiply 2, 1, 1, 2, what we're going to have is 2 times 3, 6, plus 3, that will be 9. And the second row, 1 times 3 is 3, plus 2 times 3 is 6. That's another 9. If I take out 3, that will be 3 times of the original vector v. Let this v2 equal 3, 3, which is at the diagonal direction. See, on this diagonal direction, it is just stretched 3 times longer. That's why this lambda 2 as the eigenvalue equals 3. So if you matched all this computation to the simulation, what you see, now you figured out, oh, eigenvalue, eigenvector, they're really not that complicated. They have all clear geometric interpretation.